Okay, hi everyone. Last time we spoke about the shape operator, and the shape operator we saw was somehow encoding the curvature of the surface. Today we want to talk about really like make that precise and like really extract some numbers out of the shape operator so that we can say, like, for example, that surface is like has like a higher curvature than some other surface, or compare them and something. I would like to start with like a little bit of a joke. Who of you prefers like Pepsi and who prefers Coke? Like who's in the like area of people that like I say like I'm the Coke person? Like like Coke, you know, like the Coca-Cola. Like, can we translate somewhere? Like, okay, so who is in the Coke? Who prefers Coke? Okay, only the rest prefers Pepsi. Okay, maybe after that movie, like everyone interested in geometry might like prefer one of them. Good. As I said, like just like a joke, but it shows you that like knowing something about curvature also is helpful if you go into advertisement and marketing. So yeah, like now let's start with the fun mathematics. And as I said, we want like to extract the curvature, like some kind of information, some numbers out of the shape operator. So that's where we are. The first topic for today will be what is called the normal curvature. That's one way to extract a certain number out of the shape operator. So the problem is, what we have seen is like that the shape operator at some point, which is a linear map from the tangent space to the tangent space, measures the curvature of the surface. But that's a linear operator. So we would like to extract numbers from that linear operator. So that's like this general scheme for the next few lectures will be like discussing certain ways to extract numbers from like this linear operator. The easiest way, or most direct way, would be that we choose some frame. So like E1, E2. So choose a frame adapted to S, and then consider what we already defined, like the matrix, where we put like the EI and AJ into the second fundamental form, and that's by what we have seen is nothing else than EI times the shape operator at some point P applied to AJ. So that's one way to extract numbers. So these numbers, these are just like numbers for I and j, these are numbers. So that would be a direct way. The problem is that these numbers depend on the frame that I choose. So that's the disadvantage. They depend on the frame. So if I choose a different frame and I calculate these numbers to a different frame, then I get like something that is completely like different. And the transformation laws between them is like very complicated. It's in a complicated way. So we would like to extract numbers in a little bit more intelligent way, such that we don't need like to choose a frame, for example. And one way is like the normal curvature. Another way. So the idea here is that we just try to figure out, at least like in one direction, the curvature. So that, like, for example, that you say, like, okay, like, I'm moving in a certain direction, and I would like to know the curvature in that direction. And like the problem is still is that the second fundamental form depends on two entries. So the idea is to say, okay, let's evaluate the second fundamental form only in one direction of like both entries we plug in the same vector. And because we want to, so that will be our direction, and because we want to only say like a direction, we say that it's not normalized the unit vector. So unit vector means that if I take the norm of u, I get 1. So that's like our direction. Then the expression that we get of kappa p of u, which will be defined as we take the second fundamental form and we plug u into u. And that's equivalent by recalling the definition of the second fundamental form to be given in terms of the shape operator, where we evaluate the shape operator on the vector u and then take the inner product with u again. And that's called the normal curvature in the u direction at the point P, of course. So that's a definition, and no one can forbid me to define that object. So first of all, we have to clarify certain things. First, one of them is like why it's called normal. The second one, what does it has to do with the curvature? So that's like one thing. Also, like what is the geometric meaning of that? And I would like to start with the geometric meaning of this expression. Namely, you can imagine what is happening. We have P as a point somewhere in our surface, and we give like a unit direction u, and then S of P of u, we have to calculate this expression. It's just like some other vector, which is just like might be in a completely different direction, might have a different length. And then this expression of u times sp of u is just a projection of that vector onto the u direction. So what you do is you take the orthogonal projection of that vector onto the u direction, and then this length here is kappa p of u. So u was like completely arbitrary, so that can be like an arbitrary unit vector. So I can draw that like a bit schematically as like, okay, sorry, I have to start again. Wanted to have some space, but so u can be an arbitrary vector from the units here, and as I said, for every of these vectors we get a different vector S of P of u, which would be going here, and then the projection onto onto the u-axis gives you the kappa p of u. So now you can do that for every vector u. You can play that game, and you get a different vector sp of u. And in general, what you end up with will be some kind of like ellipsoid. So that's like you take a different vector, and then you end up at a different point again. That's u prime, then you might end up, let's say, at that point with sp u of prime. So you can think of the shape operator, if you want to visualize it, you can think of that as like you take the unit sphere, and then you just like apply sp in the unit direction, and then you just like record where the vector is, and then you get like instead of a circle, you get something that looks like an ellipse. And you can see that it somehow like has like some symmetries, because sp of u, like if you like put like, for example, minus u in here, then you see that you get like the minus cancels, because that was a linear operator. So it's like invariant on the exchange of u with minus u. So that gives you, for example, one of the symmetries of like that. Like you have a point here, then you also have a point there, something. So that's like a geometric way to visualize like what's happening, this sp operator, and to give you some geometric idea of the kappa. So that's one way. And another, what we can do also, we can, of course, calculate it in an example. And for example, we had like last time, we had that S equals to be the graph of a function of f, x and y. So the c coordinate is given as fx of y. So that was, we looked at these kind of objects last time, and we calculate the shape operator for that case. And then if you insert the shape operator from last time in this expression, what we get is that kappa of at the point 0 in the direction which was given as v1, v2, and 0. So that's a general direction. And then they are normalized to have unit length 1, say. And then what you can calculate from the formulas last time is that this normal curvature has the following form. So you can calculate the curvature in that case very explicitly in terms of the second derivatives of the function. And in general, you can always express a surface near some point as like the graph of a function. That's always possible, just by taking the tangent direction and then projecting, essentially. So that gives you some idea of like how the normal curvature looks like. Namely, it's given by a certain bilinear form, which is like expressing the Hessian, essentially. So that's like sometimes good to know. So what I've not explained yet is like why it's called normal curvature. Like both words need some explanation. Why is that like a curvature in some sense, and what is normal about that? Except that like the shape operator itself depended on the normal derivative. So let's have a look at that. so the point is that it's related to a curve. So we choose C is a unit speed curve. In S, then we can plug in the tangent vector of that curve into the normal vector. So we want to calculate the normal curvature of C of t. Since C of t is a unit speed curve, the tangent vector is like a unit speed vector, and then we can plug that in. And now we want to calculate that and see what happens, and then relate it to the curvature of the curve. So that's by definition nothing else than C of t times the shape operator of P applied to C of t. That's by definition. And last time we have seen that there is a nice expression of inner product of that time, where we can essentially bring over the one derivative here over there, and what we get is that we have an inner product with the normal curvature, the normal at the point of C of t. So what you see here from that expression here is that this one is now the projection of the acceleration or if you want, like in some way, the curvature vector. Since what we learned last time about the curves was like that, like the curves measured also the curvature by, like in terms of their acceleration onto the normal. So that's how you can think of that, is that you take the second derivative of the curve, project it onto the normal, and that gives you a number, and that number depends only on the speed of the curve or the direction of the curve. And then you call that the normal curvature in that direction. So that's the explanation, essentially, why we get like something that is called normal. And to make the connection to the curvature a little bit more clear, remember that like the second derivative of the curve was related to the curvature of the curve times the normal vector of the curve, and then we have here the normal vector of C, and we can write that, of course, as that inner product, as because both of them are unit vectors, just as the cosine by the angle is between n of t and C of t. So that's, here is the curvature of the curve, seen as a curve in R3. So just like a normal space curve, and that one is the normal vector of the curve. And that's, just for completeness, is the normal vector of the surface. So that should explain a little bit, at least, why we call that that expression here, why that is called a curvature, and why it's called normal, because it involves essentially the relation between the normal vectors of the curves and the normal vectors of the surface, and is then proportional to the curvature of the curve. So, like one way to see that formula, like a little bit more in practice, is like the following. Imagine you go out in in a desert, and everything is very flat. So as far as you can see, everything is flat. There are no mountains or anything, and you just keep going straight in the desert. So what you end up with is that it's very easy for you to walk, and you say you walk in a straight line. For you, it looks like a straight line, and you don't experience any curvature. If someone was to ask you do you experience any curvature? You say, no, I'm walking straight in the desert. There's no curvature, there's no mountains, nothing, I just walk straight. But if you now are an alien and you make a look from some spaceship to that guy walking in the desert, it looks like that he is slowly working on a great circle on the Earth. So for an alien, it looks like that of course you walk on the surface, so you have some curvature, which is just given because the Earth is curved. So there's an apparent contradiction is that, as a person on Earth, you say okay, I'm not experiencing any curvature, but someone from the outside would say, no, you experience clearly some curvature because you walk on the Earth. And that's this part here measures the curvature that is seen from the alien perspective. So in that, that's the perspective from the outside perspective, where you can see it from when you really consider the surface being embedded in some space, and you look from the outside. But because an ant or some person walking on the surface will never be able to measure the normal the vector field, be able to relate this inner product. So someone working on the surface is never able to measure that quantity. So it's really something that is related to the outside perspective, and we could also project here in some way to the tangent direction, and then we would get something that is called the geodesic curvature. So that's maybe as an outlook for the next, at some point we will define something that is the opposite of the normal, which is then called geodesic curvature. So it's the outside projection. So it's it's the normal direction. Okay, so we got a little bit further, at least in the sense of that we now have a function that only eats one vector. So this, we can think of the normal curvature as a function that takes a point in the tangent vector at that point and gives us a number. So that's already a little bit better instead of a whole linear operator. But we would like to go one step further and really extract numbers. And the simplest way would be to say we just take the maximum and the minimum that we get as we vary the direction. Oh, maybe first. Extreme case, maybe that's still interesting. If the normal direction is plus or minus the normal of the curve, in that case, this inner product there just is plus or minus 1, and we get the following picture, namely that if you measure in a certain u direction, then the surface, or the curve, the curve in the surface, looks a bit like this, while the normal direction. It's like in the up direction, and in this case we get like that the curvature of u is bigger than 0. So then you get like a picture like that, that the curve is like slowly bending towards the normal direction, and the normal direction in that sense, like, and oppositely, if like n goes in this direction and the normal of the curve goes in the opposite direction, then we have a case like this, and in this case, kappa of u is smaller than u. So again, like the curve always goes in this direction. So that's the curve C. So you see, like, if once you fix the u, you choose a curve in the surface that goes in this u direction, at least tangent, and then around that like surface, you can like see if the surface goes up or down in this u direction as given by the kappa. And the kappa measures essentially how fast you're getting away from, like what is like the curvature of that parabolic expression is given by the kappa. Okay, so as I said, like the idea now is to extract the maximum and the minimum of the normal curvature as you vary the unit vector. So we get like two numbers. As we change u to be an arbitrary vector, that gives us like a function for every vector, and then we take the maximum and the minimum of that. And these are called the principal curvatures. And they're usually denoted by kappa 1 and kappa 2. Kappa 1, kappa 2. And we have two vectors that realize these minimum, and these are called u1 and u2 are called the principal directions, or principal vectors. So that's, and like there's just for like a side remark for the mathematically oriented audience, of course we have to check that there exists a minimum and a maximum, but that essentially follows because here we restrict to unit vectors, and then by compactness, a continuous function on a compact set has to have like a maximum and a minimum. So that's like ensures really that we have like two numbers which are really realized also by two vectors. And if you know a little bit of linear algebra, namely by the principle principal axis theorem of linear algebra. So if you know that, it's awesome. If not, then you just accept the following statement, namely that kappa 1 of P, or kappa 1 and kappa 2 are eigenvalues of the shape operator at P. With eigenvectors u1 and u2. So what this means is that we have our shape operator, and we can apply that one to this vector u1 that we to one of these principal directions, and what we get is that it's kappa 1, which depends on the point, times the vector again. And similarly, if you apply it to u2, we get kappa 2 of P times u2. So we get these two relations. And there is another nice property that these vectors have to be orthogonal. Over u1 is orthogonal to u2. So what this means is now what we got in summary is that if you plug in these u1 and u2 directions in the first fundamental form, because they are orthogonal and they are normalized to have unit 1, what we get here is that it's just like the entity matrix. And moreover, if you plug in these vectors, we get in the second fundamental form, because they have the property that they are u1 and u2 times like the vectors, and they are orthogonal. What we see is that like the matrix that we get is also particularly simple. So from a mathematical viewpoint, what we did here is we have like in general, we have a matrix, a 2 by 2 matrix, which has some entries here, like on 4 entries in general. And what we now did was like finding a change of basis such that this matrix is like written as a diagonal matrix. So that's why this linear algebra comes in forms of the principal axis theorem of linear algebra, which tells you that you can do that for every time you have a symmetric 2 by 2 matrix or a symmetric in general, you can always transfer it to like the diagonal expression. So that's what we did here. And we have the nice like geometric interpretation that these directions, u1 and u2, are the maximum and the minimum of the normal curvature. So if you can go back to the picture up here, so same setting, we have a vector u, and we apply it, and then we get a vector sp of u. So that's the picture. And then we look at like the minimum and the maximum, and it turns out that these ones are in the ellipsoid picture, you can see them by just taking like the direction of where the minimum is, and the maximum is like, it goes in this direction here. So that would be the maximum is like the greatest one, that would be U1, and the lower one would be U2. And that theorem tells you these both directions are orthogonal to each other. And moreover, you have here, you stretch by kappa 1 of P. In this direction, you stretch by kappa 2, and here we stretch by kappa 2. And then every other vector, you can like just imagine as applying both of these things, where we essentially expand them as a linear combination of these two vectors, and then expand one of the coordinates by kappa 1 and the other one by kappa 2. So that's like how we get now our ellipsoid. So it makes also sense, right? Like in order to describe an ellipsoid, all that you need to know is like where are the axes and how far are the axes off. That's all the information that you need in order to describe a nice ellipsoid. So that's like these two information. It's like in which axis, which is like in which is the orientation of the ellipsoid, and then once you know that, you need to know how far they are like stretching each of these one directions. So that's the geometric interpretation of these principal curvatures. So let's have a look at some of the examples. So the first example would be the sphere. The sphere, which has a shape operator which was minus the identity. So once you already know that this one is minus 1, 0, 0, minus 1, so we can read off that it's already in this particular nice form, and we can see that like the kappa 1 and kappa 2, kappa 1 of P equals minus 1 equals to kappa 2 of P. So in this case, we have like both of these principal curvatures, which is the maximum and the minimum. They are always minus 1. And it also doesn't matter which frame I choose, because like the sphere is round. So there's no particular, no particular direction which is like special. So that's one example. The other one would be the saddle. So let's see if I can draw that on the blackboard. So it's like the horse saddle. So imagine a horse and you put a saddle on top of that. So in that case, you have one direction which is like going down, and the other direction is going along the saddle, like upwards. So that's, say, like maybe U1 and U2. And if you compare it with these pictures which I just had here, you already see them still. Like one of them is like that the normal direction goes up, and then you have one of them is positive and the other one is negative. So here has 1 kappa, let's say, so that's an example where one of the curvatures is positive and the other one is negative. So so much in terms of like examples. So now we would like to know how, like we know that now for the principal directions, the second fundamental form looks very nice because it's just kappa 1 and kappa 2. But in general, you might have like some different vector, which is like not in one of these two directions. But we can always expand it. So since U1 and U2 are orthonormal in TPS, so we have two vectors which are unit vectors and orthogonal. They are especially a basis. Every vector TPS, every vector is of the form V equals to V1 U1 plus V2 for some numbers V1 and V2. And if this one, if we require that the norm is equal to 1, then this one is equivalent to V1 squared plus V2 equals to squared, because U1 and U2 were like unit vectors that are orthogonal. So we can solve this equation, then say V1 equals the cosine of some angle and V2 the sine of some angle, where the angle is given is just like the angle between like the vector V and say like U1. So that's we can always, like our vector, a unit vector is just like a rotation by some angle of the vector, say U1, U2. So we have that might be a U1 here, U2 here, and then if you have a different vector V, then this one is given by some rotation by some angle of U1. Okay, so now we know how every vector looks like. Now let's calculate the normal curvature in that direction. So normal curvature in that V direction. So just like well, I don't know what else to do than just use the definition essentially. And now we expand. We just use this equation that we have here and plug this in. So we get cosine theta U1 plus sine theta U2. And now kappa 1 plus sine theta. So nothing happened now, it just like inserted the definition of V. But now what we have is by linearity, the S operator jumps on U1 and U2. But on U1 and U2 we know what S is. namely it's just kappa 1 times u1. So what we get here is that it's kappa 1 p times cosine theta u1. So that's the first term. And then we get the same expression with kappa 2 sine theta u2. So in the u1 and u2 direction, this operator, just like scales, that was by definition like the operation of that operator on u1 and u2. Okay, and now we use the fact that u1 is orthogonal and normalized to have 1. So this u1, if it hits u1, then it gets like the norm 1. And if that u1 hits that u2, we get 0. So the cross term is vanished, and what we end up with is that it's kappa 1 times p cosine squared of theta plus kappa 2 times sine squared theta. So that's an important formula which tells you, once you know like that the vector was rotated by a certain angle, and you know the principal curvatures of the surface, then you know automatically the normal curvature in that particular direction by this formula. I think it's called, sometimes it's called the Euler formula. But I'm not the biggest fan of calling that also Euler, because there's so many Euler formulas already. So, so let's have a look at like what happens in this particular case where we describe our surface, at least locally, as a graph of some function. So we mark if the surface is given as a graph of a function of two variables, this is equals to 0, then Taylor expansion says that at least in some neighborhood, the C is given